To increase the strength, so there is a mechanism called the R1 looping mechanism. The particles are incoherent or semi-coherent with matrix. The obstacle strength is increased because the increase of the lattice field and the size of the particles. Then the dislocation line cannot cut through them. Rather, it loop them to left a dislocation loop behind. So we increase the strength this way. So that's exactly what have been done in the past. Classic ultra-high strength steels are primarily hardened by incoherent or semi-coherent particles. They are, carbide or nickel-3 moly, as I just mentioned before. The most successful cases of R1 looping strength mechanism is the invention of the 300mm and 800 steels. 300mm strengthened by carbides due to its relatively cheap, low cost, and the efficient combination of the strength and toughness. They are widely used for civil aircraft as landing gears. Chinese C919 airplane still using 300mm to make these landing gears. A100 steel is strengthened by nickel-3 moly or nickel-3 titanium via high alloying. The cost increased 5 times, but the strength, the yield strength, only increased 200 megapascal. This steel are widely used as a landing gear for the fighter airplane, including F-22, F-35, and so on. So the overall mechanism is actually very successful. However, if there is a conflict between the strengthening and the toughening, as I shown by this equation, the obstacle strength is proportional to the lattice fit and the size. Larger lattice fit give you the higher nucleation barrier. So your particles, it's very difficult for your particles to nucleate. So resulting in a very low density of the particles. And due to the higher nucleation barrier, those particles tend to nucleate around the T-facts. So that's the reason why normally we end up with a inhomogeneous distribution of this incoherent or semi-coherent particles. On the other hand, the cracking strength is inversely proportional to the size. If you increase the size, you reduce the toughness. More critically, as I said, there's a large elastic strength field generated around the interface. So where the crack will be easily initiated, give rise to premature fracture. That's the reason why you always see, the localized deformation behavior for this high strength materials. This is the reason why we normally see this kind of a banana curve with the increased elongation. You see, the yield strength drops. This kind of trade-off become more severe when you go to the higher strength region. So very difficult to further increase the strength without sacrifice of ductility. So our looping mechanism touches the same, because you see the A310 steel should be the next version of the A100. The strength increased by 100, 200 megapascal, but the toughness dropped to 50, below 50. You, as the left image shows, have you done this? So here I'm going to show the first part of my talk. Ultra-high strength shears hardened by coherent ordered nanoprecipitation. The key word here is ordered. We select nickel aluminum intermetallic compound as the strengthening medium. This compound is strongly ordered. Nickel atoms have to occupy the vertex, while the aluminum atoms have to take the central position of the lattice. Very important, the antiphase boundary energy of this compound is very high, 0.5 joule per square meter, while the interface energy is very low, 0.05 joule per square meter. So when the dislocation cutting through the particle, the interface will transfer from the low energy state, which is ABBA, to a high energy state, AABB. Then the optical strength actually transfer from the elastic strength field to the chemical effect. The equation has changed, as I expressed at the bottom. So we take advantage of the high antiphase boundary energy here, use the chemical effect to strengthen the material. So our approach here is we lower lattice speed to promote precipitation of the strongly ordered nanophase. As I mentioned, this compound has a high antiphase energy, will give you high optical strength. If you further lower the lattice speed, you can get massive nanophase precipitation with a fine structure. So sigma this, you can achieve the ultra high strength. But how to suppress the planar slip, which is the typical characteristic of the ordered particles? How to suppress the planar slip? What we have done is that we retain the high density dislocations generated during the aging, of course, because of this existence of this ordered nanophase. Then the interaction between the existing dislocation with the massive nano precipitation may give us good ductility. Okay, here shows the composition of our sphere. Iron nickel aluminum moly with a little bit niobium. The very important addition is the moly. Addition of moly further minifies the lattice speed because moly has zero solubility in the nickel aluminum, and it mostly dissolved in the matrix. It has a large atom size, so it increases the lattice parameter of the matrix and reduce the lattice parameter difference between the precipitate and the matrix. So as with the increase of moly, you reduce the elastic strain energy and as well as the lattice speed. Here shows the typical microstructure of our newly developed sphere, annealed at 500 degrees C for 4 hours. As indicated by the blue arrows, you see many tiny precipitates embedded in the matrix. Another thing I want to emphasize here is that you see a lot of the transformation dislocations retained in the matrix, as indicated by the red arrows. So that means these dislocations did not fully recovered as usual. The hiding image taken from 100 and 110 direction confirm the B2 ordering nature, as indicated by this red arrows here. Another thing I want to point out: three-dimension improved tomography results confirms the ultra-high number density of the precipitate is close to 3 times 10 to the power of 24 cubic meter. So that means every 8 to 10 nanometer, there must be a nanoparticle there. Of course, due to this huge number, the distribution is homogeneous everywhere. The key thing here is that morning atoms tend to segregate around the nanoprecipitate because of the limited solubility. So due to the formation of this nanoprecipitates, moly got rejected from these particles and segregate on the surface to form co-shell-like structure. That's very important for this material. I will discuss this later on. Here shows the mechanical properties of this steel. As you see, the yield strength is about 2 gigapascal, and fracture strength is around 2.3 gigapascal. Compare with the 300M and A100, the yield strength increased by at least 200 megapascal, and the fracture strength actually increased a lot. For the first time, we obtained the homogeneous ductility in this material, in ultra-high strength material, 7%, larger and working harder capability. We have calculated, the strengthening contribution for the different mechanisms, as shown here. This contribution from the elastic strength field become very limited, below 15 megapascal. The major contribution is from ordering effect, which is close to 1.1 gigapascal. We can calculate from the textbook, based on the equation in the textbook. So this confirms why our material has a high strength, because this ordering effect. Then the other question is why we can have homogeneous ductility in this material. We have checked this material by using the high energy X-ray diffraction. As shown here, the misfit is really low at the onset of the precipitation. The misfit is only 0.03 and increase a little bit to 0.17 after aging. Very important here is that based on the width of the peak, we can derive dislocation density of inside the material. The retained dislocation density is really high, 10 to the power 14 per cubic square meter. It's really high. And due to the low misfit interface and the low interfacial energy, the precipitation kinetics of this nanoprecipitate is really quick. We have, carried out the in situ scattering experiments at a different temperature. Then we fit the data by GMA equation. The time epsilon n equals 0.7, which is much larger than that of the other precipitation emerging steels, usually 0.2 to 0.4. Indicates that the precipitation is dominated by rapid nucleation and interface different contrast growth. It's really quick. So that's the reason why we can retain the dislocations, because Due to the fast precipitation of the nanoprecipitates, they effectively pinned the transformation dislocations, so prevent them from the recovery. Then during the deformation, as seen here, on the left shows these conventional planar sleeves. You see, there's a single dislocation source, the sleeve on a specific crystalline plane, crystallographic plane, and stopped by dislocation pi r. That's conventional planar sleeve. In our case, you see a lot of dislocation reactions, penetrations. So when the dislocation line cuts through the particles, they will meet the existing transformation dislocations. Then the dislocation will generate, they interact. So make the planar sleeve switch between the different parallel crystallographic planes rather than concentrate on the one single crystallographic plane. So by doing so, the plastic flow would be homogenized. So here summarize the strand mechanism for our material. You see, when the first dislocation line cuts through along the specific crystalline plane, it cuts through, then you will, encounter the existing transformation dislocation line dislocated there and form the elastic strand field as indicated by the red symbol. When the dislocation second time cut through these particles, when the dislocation line met this, this red spot, they will switch to another parallel crystal plane. So still, this planet are not on the same plane, it's on the parallel planes. So this gives us the strong work hardening capability, and the homogenized plastic flow give us the large homogenized ductility. So this mechanism is totally different from what we observed in the past. For our material, as you see, with the increase of yield strength, toughness is increased, as indicated by the red line on the right figure. For the rest of the material, you see, with the increase of yield strength, toughness is decreased. The fracture graph shows that the fracture mode actually transferred from brittle cleavage fracture to ductile void condensations. So this why we have found that this is due to the synergy effect of ordered nanoprecipitates and the monodecorate coherent structure. So now I move to the second part, the second case of my talk. Superior irradiation tolerance from coherent ordered nanoprecipitation. As mentioned earlier, to reduce the carbon emissions and solve energy crisis, we have to improve the clean energy efficiency, such as nuclear energy. So we have both fission and the fusion reactors have to work at a high temperature with a high neutron flux. This require material to be stronger, tougher, and also more nuclear irradiation tolerant. Under radiation environment, the material properties will be degraded due to the void swelling, radiation hardening, and embrittlement, as well as the irradiation creep. The damage actually arises from the preferential flux of eliminate these side effects from the irradiation. Misfit interface are regarded as the key to enhance radiation tolerance. By introducing numerous misfit interfaces inside the material, the defects generated by irradiation will be sank or trapped by this misfit interface, so give rise to higher radiation tolerance. So in this regard, actually, ODS steels, which contains numerous misfit interfaces, showed the best radiation tolerance so far. However, this high energy interface are intrinsically unstable at high temperature with a high dose irradiation. The oxides actually gradually shrink and until finally disappear. So this dissolution will degrade the material property. As I just mentioned in the first part, our nanoprecipitates have a low energy interface, so the capillary force should be small, and the multidegrade interface highly stable because the moly has the lowest diffusion rate in the I matrix. So kinetic moly segregation will slow down the diffusion of the elements. That's the reason why the particles are highly stable. And also, its precipitates have a very high number density. So can we use this nanoprecipitate, we call it super lattice, to prevent the irradiation damage? So we have conducted the irradiation test for this newly developed steel. To our surprise, this CityU shows zero void swelling at 500 degrees C up to a very high radiation dose of 2,350 dPa. In comparison, the typical ODS GDL of 840 dPa test at the same temperature, you can observe a high density inside the material, high density of voids inside the material, and as shown on the right image. This outstanding irradiation tolerance was observed in a relatively wide temperature range between 400 and 600 degrees C. Even for the 600 degrees C sample, up to 2,350 dPa, we didn't see any void formed. So then the question is, why this kind of superlattice can prevent this irradiation tolerance? And here shows the evolution of lattice and nanoprecipitates during the high dose irradiation at high temperature. You see, even after high dose irradiation, massive nanoprecipitates still there. They didn't dissolve, which is different from the ODS sphere, oxides in the ODS sphere. The number density is reduced a little bit, as shown on the left bottom image figure by the black curve. That the number density is reduced a little bit, size, while the size remains same. We have checked this nanoprecipitates by hybridization TM. They are still ordered. They still have the lattice, ordered lattice. Very important, there's some disordered solute-rich regions emerge totally different from our scenarios previous. We make best use of this precipitation kinetics, fast precipitation kinetics, to produce this dynamic ordering disorder process. By doing so, we can obtain the superior irradiation tolerant materials. Okay, I have a few minutes left, so now I'll pick to the last case. Bulk high performance ultra-fine grain trip steels by coherent now is disordered nanoprecipitate. In the previous two cases, we used this ordered nanoprecipitates, but in this case, we use the disordered nanoprecipitates. So why trip steel? Trip steel have superior formability, hardenability, and high fracture strength. So they are very promising for lightweight strategy and crash safety in automobile industry. So the energy absorption performance of trip steel is about twice higher than that of high strength steel and 1.5 times higher than the trip steel. But there's a big problem. The yield strength of this steel is very low, only 300 to 400 megapascal. The industry is at least 700 megapascal. So that means the grain size of the material needs to be reduced to below 1 micron. Nevertheless, there's no mass production line available for mass produce this ultrafine grain steels. And the high pressure torsion and equal channel angular process and so on, they can apply to this material to produce the ultrafine grain trip steel, but very costly, and the sample size is limited. Cannot make those the components. Okay. Another challenge is ultrafine grains are usually unstable because of high energy there. So how to make the material stable? Our approach is that we use this disordered nanoprecipitates because it has a very low interface energy and low nucleation barrier. So we can end up with the many precipitates. Then they can provide higher than pressure due to their weak constant dependency. The structure is stable. They have a low misfit, relative misfit with the matrix, and they are disordered, so they have weak dislocation, weak interaction with the dislocation, and so we can pin grain boundary movement, but not pin the dislocation movement. That's the key here. So there are a lot of systems available: iron, copper, and copper system. There's exists a miscibility gap. So you add in the copper into the iron, generate miscibility gap, and copper will precipitate out very quick during the recrystallization. So we simply add the copper into a typical trip steel. As we here, you roll your material and then recrystallize your material, and you obtain the ultrafine grain steel. The grain size is 800 nanometer on average. Then you check the material by the hardy, you can see massive copper nanoprecipitates formed, and they effectively pin the ground boundary moment. And also on the ground boundary, there's no particles, except for some enrichment of the carbon. And as a result, the yield strength increased 300 megapascal, without sacrifice any ductility. To our surprise, the working hardening capability become more pronounced and the ductility is even increased. So this material shows the best product of accomplished 95%. So here shows the interplay between recrystallization and precipitation. The precipitation did not interfere with recrystallization process, and the on the right shows the inner pinning of the grain boundary. So that indicates the precipitate do pin the submicron grain grooves. And here calculate the driving force for the three things here. One is the recrystallization driving force, the linear pressure, and the driving force for grain growth. As you see, at 1 minute per minute, the linear pressure is above this, driving force for grain growth. So that means this precipitates can effectively suppress the grain growth of this this material. The driving pressure for recrystallization is reduced dramatically. As is consistent with the fast process of recrystallization. The nanoprecipitates do not pin the dislocation moment and twinning. The sample, still at the early stage deformation. The sample, the dislocation still dominates deformation. And the nanotwins and the dislocation cut through the nanoprecipitate easily, resulting in the double density, actually. And also, the dislocations are frequently found inside the nanotwins and in their interface, as confirmed by bright field TM image and the corresponding laser orientation map. So actually, this is nanoprecipitates beneficial for the dislocation moment and the twinning process. That's the reason why we observe the more pronounced working hardening capability. Okay, here comes my summary of this talk. I just discussed with you three new mechanisms. One is the strengthening mechanism through the ordered precipitates. The second one is through this disordering of superlattice, and we provide a new irradiation resistant mechanism. The last one is the refinement strategy for mass production of the tropospheres. So that's all I would like to say today. I'm happy to answer your questions.
Okay, thank you, Professor Lu. It's great and very exciting talks. I do have some questions regarding radiation effect to you, but I will leave to our audience and our participant. Anyone wanted to raise? Okay, Professor Shili, one question.
It's really nice talk summarizing all these recent work from your group. I have quite a few questions, but I'll start with one that's on the first example you illustrated. And I noticed that when you compare your ultra-high strength steel versus M300, M300 goes down actually, so it's kind of softening, right? And you introduced this massive number of precipitates and the dislocation. So do you think? I realized when you mentioned your main goal is to overcome the toughness. So you introduced this kind of very novel microstructure and chemistry and so on. was did you achieve a high fracture toughness? Was it because of this entanglement of precipitates and dislocation that basically lead to a very large ductility, very large work hardening? Is that the reason? I'm just trying to piece all these together. Maybe you can tell me the answer.
Okay. Thanks, Srini, for the nice question. Okay. Actually, as I show here on the right figure, pH 13.8 also, hardened by nickel aluminum. But it has very low fracture toughness. We observe that to achieve the high toughness, we have to add this moly inside to it. The moly actually creates some moly cluster on the surface of the nickel aluminum. So that's the key. So we have to optimize the heat treatment process to achieve the high toughness. But in our case, the good thing is that by doing so, we didn't sacrifice the yield strength as Europe. So we can increase the toughness and the yield strength at the same time. So that's, but the mechanism and behind this toughness issues, we are still digging out the real reasons. Yeah. Okay.
Any other questions? Yes.
Hello.
Yeah.
Very nice talk. And I have a small question about the irradiation tolerance. So I'm curious about how about the irradiation tolerance of the coherent tube steel.
Recording in progress.
The high seven, 800. For your radiation.
Yeah, you're expert. Actually, we say when we test the 700 C, the bad thing happened. The nano precipitate going to cause an oh, 700 degrees C.
Recording in progress.
And after fracture, so we come up with conclusion with this indirect evidence, not the direct evidence. We didn't calculate the back stress.
All right, thank you.
Okay, we didn't get any questions from the internet, so I will stop here. Let's thank Professor Lu again.
Thank you. Thank you.
It's a great presentation.
Yeah, it is very pity to me. I'm not able to be in person to give this talk. See you guys later.
I wish next year we can have
you guys in the future, near future. Yeah. Okay.
Thank you. Okay, so our next speaker is Professor Peter Liao. Most of us know him very well. Okay, Professor Liao is currently endowed chair professor in University of Tennessee, Knoxville, in material science engineering department. Professor Liao graduated from Taiwan National Tsinghua University, which where I graduated from also. Okay, but he's several years. We know very well. Let's welcome Professor Peter Liao, and his title: Advanced High-Entropy Array Design and Fundamental Understanding aided by Neutron Scattering. Let's welcome Professor Liao.
Thank you very much for your introduction, Professor Kai. It's certainly a pleasure to see you here.
Recording in progress.
In Dr. Fong is part of his thesis. Dr. Chen, Dr. myself, we are from Oakland and certainly Department of Material Science Engineering at the University of Tennessee. First, I would like to say thanks for the financial support. They are from National Science Foundation, Center for Material Processing. First, I would like to
Recording in progress.
Materials, which can also and compositional complex alloys, base alloys. One of our team members call it metal buffet. They are disorder, and however, they are structurally ordered. And if we base on the definition of high entropy alloy, this year's classic work as shown here. The first definition on the composition, the number of major elements should be equal or larger. The atomic percent of each element should be between 5 to 30. Also, some minor element present in the material. We can also element with atomic percent less than 5%. If those materials are of the body center cubic, and also hexagonal close-packed type structures or combination of some of them. The second definition is based on a configuration entropy. That is, the entropy should be greater than 1.5 R or is a gas constant, no matter they are single phase or multi-phase type materials. Since it's a high entropy alloy, so there are some attribute for this material. As mentioned to you before, it's a high configuration entropy. It has a severe local lattice distortion because of the presence of different atomic sizes. It also has this heterogeneous local atomic environment, such as short range order. and possible sluggish diffusion, which is certainly still a critical issue to discuss. Because of their nature, it has a vast compositional space. We can tune, for example, the stacking for energy. Therefore, we have a twin-induced plasticity trip and transformation-induced plasticity trips, as briefly mentioned by Professor Lu's nice work. They can also have this ductile multi-component intermetallic nanoparticle. And this work was really done nicely by Professor Tao Yang, Professor Kai, and Professor CityU's group here at City University. And we certainly like to have this integrated engineering concerns, and such as can we develop lightweight and low-cost materials? If you want to contrast the stainless steel and high entropy alloy as shown here, the 304 stainless steel, we have about 67% of ions and 2% of manganese, 19% of chromium, and 7% of nickel, 4% silicon,